In the unit when we introduced the AMD GPU architecture, we mentioned that memory coalescing is a very useful tool that may improve the GPU performance. So here, let's look at how to write your program to utilize this feature. We're going to look at this example of matrix copy, and we're going to implement matrix copy in two ways and see what's the performance difference. Let's say for matrix representation, in GPUs, it's typically just a trunk of consecutive memory. But there are two different ways that we can represent a matrix. We can either store it in a row measure that these elements are organized in the way that is shown in the figure. Or we can organize in a column measure that we organize the element on the right side. So for a regular GPU implementation of matrix copy, it basically has nothing to do with a matrix layout. We can just consider it as a vector and copy element by element. But for this example, I just want to show you the difference between how we access memory, so let's just consider it as a matrix. So typically, we want to implement the matrix copy in this way. We call it matrix copy good. So we have four arguments. The first one is a source, next one is a destination, and we also pass in the width and height of the matrix. We find the ID of the element. Then we find the x coordinates and the y coordinates according to the ID. If this coordinate falls within this matrix, then we copy from the source to the destination. It's a very simple implementation. It's even a little bit more complicated because we actually do not need to consider its coordinates. But this is the most natural way to write this program. And let's analyze if we can enjoy memory coalescing. If the ID is 0, we're accessing the element 1 in the matrix as in the figure on the right. If the ID is 0, we're actually loading the data represented by the number 1 in the figure on the right. And if the ID is 1, we're moving to the right, we're accessing element 2 in the figure in the right. Because our matrix is row measure, adjacent thread is accessing adjacent data. Therefore, our program can enjoy memory coalescing. But what if we have a row measure matrix, but we mistakenly consider it as a column measure matrix? So as you can see the comparison, we swap this divide sign and this percent sign, and we consider the height rather than the width. So just by changing this little bit code, we will see a huge performance difference. So we tried this program on MY100 GPU with a matrix that is 32K by 32K. For the good implementation, it only takes 9 milliseconds, but for the bad implementation, it takes 364 milliseconds, which is 40 times slower than good implementation. This is because we're not utilizing memory coalescing. So let's explain memory coalescing again using a figure. Assuming we have two threads, one thread is accessing address 0 and the other thread is accessing address 4. Because address 0 and address 4 actually fall within one cache line. And the smallest unit that a core access a cache is by cache line. So these two memory access can be combined into one memory transactions. And we only send one memory transaction that is fetching data from 0 to 31, although we only need 8 bytes of data. And then if the third thread is accessing address 16, we do not need to add any extra memory transaction. The address 0 to 31 still covers address 16. But if the next one wants to access address 98, we need to bring in a new cache line. The number of memory transactions actually can increase the latency. And also because we're loading a lot of data to L1 cache, we're also going to pollute the L1 cache space and force some useful information to be evicted from L1 cache. And then, if we consider another case, if these addresses accessed by the different threads are not next to each other, they access different addresses in different cache lines, we're actually having to load a lot of data. We have to load 4 cache lines. So in extreme cases, each wavefront has 64 threads, and if all the threads are accessing different cache lines, we need to load 64 cache lines into the core, which takes a long time. So this tells us we need to consider what addresses that we're loading. Although we may not know the exact addresses, but at least we can know the relative addresses across adjacent threads. Ideally, we want all adjacent threads to access adjacent data. or even better, to access the same piece of data. We want adjacent threads within one wavefront to load one piece of data, or adjacent pieces of data, so that we can minimize the memory transactions and preserve the L1 cache size. And in the next video, we're going to show another example of how to use LDS to enable coalesced memory access.